But we need to understand a little bit about the nature of light in order to talk about electrons. So we do have to make a little side trip into physics here. Light is a form of electromagnetic radiation. It is composed of perpendicular oscillating waves, one for the electric field and one for the magnetic field. So you have an oscillating electric field and an oscillating magnetic field, and they are perpendicular to each other and to the direction of travel. An electric field is a region where an electrically charged particle will experience a force. A magnetic field is a region where a magnetized particle experiences a force. We are all quite familiar with magnetic fields. If you've ever used a compass, if you've ever stuck a magnet on a refrigerator, if you've ever played with Brio trains, okay, you've interacted with magnets. They're cool. They're neat. Magnetic fields and electric fields behave in a very similar way. They are not the same, but they are very similar. So you can think of the electric field as just being a slightly different version of a magnetic field. So light is a form of electromagnetic radiation. All electromagnetic waves move through space at the same constant speed. It's called the speed of light. It's 3 times 10 to the 8th meters per second. It's really, really fast. After you've taken physics and a little bit of chemistry, it can be amusing to watch the cartoons and point out all the physics violations of natural laws in the cartoons. You know, some of them, you see the old geezer and he's blowing out the candle, and then he gets in bed before the room goes dark. Not possible. Nobody can move that fast. Light moves really, really fast. Light moves at the same speed all the time. Okay, that's an important idea. So here's an illustration of electromagnetic radiation. So here we have in the red the electric field, and these travel as sine waves, so they go up and down. Here's the direction of travel. This is oscillating in a plane that's perpendicular to the direction of travel. And then the magnetic field component is perpendicular to that, so it's kind of doing a sidewinder thing here as it goes along. This is a picture of lightning striking something. We all, I think, recognize that you see the lightning and then you hear the thunder later. You see the lightning first because lightning is the speed at you are seeing it. The light from that event is moving at the speed of light. Sound moves much slower. Sound travels at about 340 meters per second compared to 3 times 10 to the 8th meters per second. And that's how you get this, concept of sort of estimating how far away is this storm by counting the seconds between when you see the lightning strike and when you hear the thunder. Because the distance that you are from the lightning strike, if you are farther away, it will be a longer time between the seeing and hearing. If you are right close to the lightning strike, it happens almost the same time. And so the farther away you are, the longer the distance between the sight and the sound. Well, there are different ways to characterize waves. And one of them is the amplitude. The amplitude is the height of the wave. How tall is it? It's the distance from a node to the crest or a node to the trough. And a node, let's just go back to this picture of, I did not mean to do that. Let's go back to this picture here. Here we see this wave going up and down. The node is where it crosses 0. You can think of this as 0, and it's going positive and negative, and positive and negative. And so the node is this center point here. So amplitude is this distance or this distance. It's going to be the same. It's a symmetrical wave. The amplitude is a measure of the intensity of the light. If it's a really bright light, the waves are going to have a large amplitude. If it's a dim light, they're going to have a short amplitude. Another characteristic is the wavelength. And this is the distance from one crest to another, or you can measure it from one node. You have to skip a node and then go to the next node, is another way to measure the wavelength. Oh yeah, see, here's the picture. So here's amplitude, and here's the wavelength. So how long is the wave, and how tall is it? They're all moving at the same speed, the speed of light, but some of them are higher, and some of them are longer or shorter than others. Frequency, and this looks like a V, but it's not. It's a nu. It's a Greek letter. So it's a kind of a curvy V, because V is velocity and nu is frequency. It's the number of waves that pass a point in a given period of time. So if you were standing over here, and this wave is going past, and you were counting the number of peaks that went past, that would be the number of cycles per second, or the number of waves per second, and that's what frequency is. The number of waves or the number of cycles. And a common unit is hertz, which is, it is a rental car company, but that's not what we're talking about. Hertz, abbreviated capital HZ, is the name of the unit that means cycles per second. So you might see 1 hertz, that means there's 1 event per second. That's a pretty slow frequency. Or you can have cycles per second, or sometimes it's just 1 per second. 1, whatever you're interested in, per second. The total energy of that wave is proportional to the amplitude of the waves and to the frequency. The larger the amplitude, the more force it has. So think about going to the ocean, and you're standing out in the surf, and the waves are coming in, right? Waves traveling on the ocean behave in many ways like waves of light do. And you think about a small wave comes and crashes over you, and then here comes a really big wave, a tall, high amplitude wave. Which one is going to knock you over? The short one or the tall one? The tall one, right? It has more energy in it. So light waves with a high amplitude have more energy, okay? The other thing that matters is the frequency. So if you're standing there and a wave, kind of maybe a medium-sized wave hits you, and it's hitting you like every 5 minutes, is that really going to affect you very much? No. What if it's hitting you like every 2 seconds, a medium-sized wave, and it's just beating on you, right? That's going to affect you more, because there's more energy when the waves are coming closer together more frequently. So the more frequently the waves strike, the more total force there is. The larger the amplitude, the more total force there is. When we're looking at waves traveling the same speed, they're all going at the same velocity. That means the shorter the wavelength, the more frequently they pass. So wavelength and frequency are inversely proportional because the speed of light is constant. You think about, oh, that's not what I meant to do. I meant to draw something. I'm not really good at drawing anything, but okay, that's my attempt at drawing 2 light waves. Which of these has more energy, this one or this one? The top one. They have the same amplitude, but this one has a shorter wavelength. If they're both traveling at the same speed, this one's going to have peak, 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 peak much more frequently than this one, right? The frequency is higher because the wavelength is smaller. Short wavelength, they're traveling at the same speed. When I look at these 2 waves, this one looks more energetic to me. Maybe I'm crazy, but this one looks like somebody jumping up and down, lots of energy, and this one looks slow up and down. They're moving at the same rate, but the speed at which they're going up and down is much slower. So high energy, means you have a short wavelength and a high frequency. The frequency is inversely related to the wavelength. Wavelength is lambda. It's another Greek letter. So here the wavelength is long, the frequency is small. I was going to say short, that doesn't make any sense. Small frequency, long wavelength. This is a high frequency because it's got a short wavelength. Does that make sense? A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. We kind of glossed over that equation on the previous page. It said that nu was equal to c over lambda, where c is the speed of light. Remember what the speed of light was? I don't know. How do I think 3 and write 8? I guess I was thinking times 10 to the 8th. And what's the unit on that? Do you need to memorize that for the test? That's a good question. I'll have to get back to you on that. So there's the speed of light, and we want to divide by the the wavelength is 515 nanometers. Are the units going to work out? No, because nanometers and meters aren't going to cancel. Here's a shortcut for doing a conversion here. I'm having issues. What about, oh good grief, I can't even erase something. Instead of writing nano, the n, what if I write what it means? It means 10 to the minus 9th, right? Now, that's not proper scientific notation, but your calculator will still understand it. So 3 EE8 divided by 515 EE minus 9 equals probably 3 sig figs, 5.83 times 10 to the 14th. And you could give the unit as per second, or you could give it as hertz. But that's the frequency of the light. Hertz. Any questions? This equation is a good thing to understand. But if you're given a frequency, something, 52 per second, and you've got a wavelength, 2 meters, never mind. That was, I don't know, it's too late to go there. I'm not going to go there. Anyway, questions? Just forget that ever happened. We'll strike that from the record. Color. Color of light is determined by its wavelength. The wavelength and frequency are related. Okay? So if we're talking about it depends on the color depends on the wavelength, and the color also depends on the frequency. White light is a mixture of all of the colors. It's a spectrum of light. And if we take white light and pass it through a prism, it's separated into a rainbow. And we see all the different colors of light that are in that white light. And this is the spectrum. It's red, orange, yellow, green, blue, indigo, violet. And it's always in the same order. And one way to remember that is Roy G. Biv. It's just, you're like, how on earth does that help me remember anything, but Roy G. Biv. Those are the first letters of the color names. Red, orange, yellow, you get the idea. Have you ever looked at a child's drawing of a rainbow and thought, there's something not right about that rainbow? Children often don't recognize that rainbows always have the colors in the same order. And it has to do with the wavelengths of light and how they get separated in a prism. So when an object absorbs some of the wavelengths of white light and reflects others, it appears to be colored. What we're seeing from objects is the light wavelengths that are reflected. So this girl's shirt is reflecting red light and it's absorbing the other wavelengths of light. When we see something that's black, that's because it's absorbing almost all of the light and reflecting very little. Something that's white is reflecting all of the light. And that's why, if you're going to be out in the sun in the summer, especially around here, do you want to be wearing all black? No, you're going to be much warmer than if you were dressed head to toe in white, because white is going to reflect the waves of light, and those waves also carry energy that can make you very uncomfortable. Where am I going with this? So different wavelengths our eyes interpret as different colors. And so red light has a longer wavelength. Yeah. And blue light has a shorter wavelength, and yellow's in between. So the wavelength is what gives us the colors. The differences in amplitudes are differences in brightness. So if it's a dim light, it's going to have a small amplitude. A bright light has a large amplitude. The wavelength, though, is what determines the color of the light. Visible light is only a little teeny tiny part of the whole electromagnetic spectrum. The shorter the wavelength, the higher the frequency, the more energy that radiation has. And so in this electromagnetic spectrum, on the opposite sides of the visible light, we have radio waves at one end, and those have very low energy. And then we have gamma rays at the other end, which has very high energy. Very high energy electromagnetic radiation can cause a lot of damage. It can damage biological molecules. It can kill you. And it's ionizing radiation. What it does is it creates ions out of some of your atoms, and this is not a good thing. It causes all kinds of bad things to happen. So anyway, here's the whole electromagnetic spectrum. And so visible light is this little tiny piece in the middle, and they've zoomed it out so you can see red light is about 750. Here the wavelength is given in nanometers, and violet is 400. So in this region, 400 to 750 is what we can see. So here's the wavelength in meters, and so that's very small. The nanometers are in here. If we go to longer wavelengths of light, then the frequency decreases. So this is a lower frequency. And so we have infrared light and microwaves and radio waves. So your cell phone, AM, FM, TV signals are down here. If we go to the shorter wavelengths, higher frequency, ultraviolet. Can ultraviolet radiation damage your skin? Yeah, it can give you a nasty sunburn, right? And we go more energetic into X-rays and then into gamma rays, and those are really, really dangerous. But what's the difference between a pretty blue light and a gamma ray that could kill you? What's the amount of energy it contains? It's the wavelength. It's the same thing, it's just got a lot more energy, and so it can hurt you. You're laughing at me, that's fine.
No, I'm not laughing at you. I never thought of that.
She laughs in the face of death. This is good. So, she does have death pants on, yes. Okay, continuous spectrum. So we shine a light through a prism and we see this rainbow and we get a continuous rainbow. And there's just the colors just blend one into the other. And I'm sure you've seen this happen. It can happen in your, it happens in my entryway. There's a chandelier that has some glass pieces in it, and when the light comes in just the right way, it sends little rainbows all over the room. The kids are like, whoa. Yeah, it happens every day. Get over it. And this is exactly the same thing that happens when we see a rainbow in the sky. The difference is that raindrops, little tiny droplets of water in the air, are causing this prism to happen and separating the wavelengths. This is an interesting picture. So we can see visible light, but we can make detectors to detect other sorts of radiation, like infrared light. Infrared light is heat. Oh, I forgot something. See this down here? Read about microwaves, infrared, visible light, ultraviolet, and X-rays. It's in your book. Read about it. I'm not going to talk about it, but you should read it. So infrared is heat, is electromagnetic radiation that carries a lot of heat. And so these night scopes, night vision things, are infrared light detectors. A warm body gives off infrared light. And so here is a man. You can see his face is red because his skin is exposed. There's a hand and his legs. And then the rest of him is darker. But we can still see him against the blue background because even though he's clothed, thankfully, heat is still getting through his clothing. And we see the dogs. And you look at this dog and you see, yes, it's true, dogs have cold noses. See that? His nose is blue. His eyes are red. His ears are red. The insides of his legs, that's where more of the heat is escaping from his body. That's kind of interesting. High energy radiation is destructive to tissue, but we can use that to advantage. We can use high energy radiation to kill cancer cells. So if you've got a tumor, perhaps in your brain, that can't be operated on because if they cut in there to get the tumor out, they'd mess you up so bad that what's the point, right? That's the problem with some tumors, is you can't operate on them because you'll kill the person trying to save them. So what can you do? Well, you can use radiation. And what they do is they take radiation from multiple directions. So each of these beams is going to be fairly weak because that radiation is going to pass through the healthy tissue as well. And it will cause some damage, but you have this benefit risk balance where, yes, there's some risk from the treatment, but hopefully the benefit outweighs the risk. And so you have some risk of damage to healthy tissue, but these are lower energy beams. But if you get a bunch of them and they're all focused on the tumor from multiple directions, then the healthy tissue damage is minimized and you can maximize damage to the tumor. So there's a lot more you can read about that, but that's just kind of an idea there. Another thing that waves do is they interfere with each other, and this is what happens when waves interact. There's two kinds of interaction, two kinds of interference. We can have constructive interference and destructive interference. If you get two waves interacting that are in phase, meaning their peaks and their troughs are lined up, then they add to each other and make a larger wave. And if you have destructive interference, you've got waves that are out of phase. The peak of one is coming at the trough of the other, and so when you add them together, they cancel out. You can see this playing with water, even in a bathtub, but maybe a swimming pool or a lake or something, and you can make ripples, and you can see how they interact, and they constructively and destructively interfere with each other. This is also the sort of thing that happens on a trampoline. Have you guys ever jumped on a trampoline? And have you noticed that if you get bouncing just right and somebody else is bouncing just right, they can send you much, much higher? And sometimes, yeah, double bounce. But sometimes it exactly cancels out, and you were going up and down, but they bounce at just the wrong time, and you just stop dead. It's the same concept of the waves constructively adding or destructively canceling each other out. So here we have two waves that are in phase, and they interact to become a higher amplitude wave. This does not affect the rate of travel. It does not affect their frequency or their wavelength. It affects their amplitude. Okay? If we have two waves that are out of phase, if they're exactly equal and exactly out of phase, they can flatline. Okay? Just completely cancel each other out. Another thing that waves can do is called diffraction. If you have a traveling wave that encounters an obstacle or an opening in a barrier that is roughly the same size as the wavelength, the wave will bend around it. And this is really kind of crazy. But waves do this. Traveling particles do not diffract. A traveling particle will either go through the hole or it will hit the obstacle, right? But the waves will actually bend around. And so we can look at the diffraction of light through two slits that are separated by a distance comparable to the wavelength, and we can see an interference pattern of the diffracted waves. And there's all kinds of cool calculations and stuff that you can do that. But that interference pattern is a characteristic of all light waves. So this is an example of what happens. Here you've got waves, and we're just showing the crests of the waves. So the wave is going up and down, it's traveling this way, and here are the crests. And as it comes to this barrier, and there's a slit here, as it goes through, the wave curves. It bends. If you have particles going in a straight line, these particles that hit the opening go straight through. The ones that hit the barrier do not go through. There's no bending, right? And this concept is going to become important later. If we have two slits, we can get interference between the light that has come through. So here we have one light source. And it is sending waves out, and these are going to be all in phase with each other because they came from the same source. Just like a ripple in a pond, this light is going to come out in a giant circle. So when you drop a pebble into a swimming pool or a pond, you see the ripples go out, the waves go out in a circle, right? And if they come to an obstacle with a little hole in it, they will go through and bend, they'll diffract. When we have two slits like this, now we have these waves, and they're coming and they are in phase with each other. And so waves that are out of phase will just make a dark spot, and waves that are in phase will make a bright spot. So what we'll see over here is at this point, because now we've separated these two, as they interact, at this point they'll be in phase, and here they're out of phase, and here they're in phase and out of phase. And we can actually measure the distance between these and the difference here and do all kinds of cool calculations, and that's physics. So one of the interesting things that happened with quantum mechanics was looking at the particle nature of light. We're just talking about light being a wave, right? It's electromagnetic energy. Well, it was observed that many metals will emit electrons when a light is shined on their surface. It's called the photoelectric effect. And classical wave theory said that this was because the light energy was being transferred to the electrons, and then the electrons had enough energy to escape. But according to this theory, only the amplitude of the light should affect the emission of electrons. So if the light was more intense, you should get more electrons, and if the light was dim, you should get fewer electrons. So it predicted that if you had a dim light, there would be a lag time, because the electrons are going to have to absorb enough energy. So the dim light, you're going to have to wait a while before any of the electrons have accumulated enough energy to escape. But what they found was that was not true. So here's an illustration of the photoelectric effect. Light hitting a metal surface will eject electrons. So you can put that metal in an evacuated chamber so that the electrons don't run into things, and put a positive electrode here that they'll be attracted to, and you will see current flow when those electrons are ejected. What they found was that there was no lag time. There was a minimum frequency, a threshold frequency. So here's the rate of electron ejection as a function of the frequency of the light. So you increase the frequency of the light. At these lower frequencies, there were no electrons being ejected, no matter how long you wait. It just didn't happen. But when you got to a certain point, they would be ejected. And at this point, if you had high intensity light, you'd get more, and low intensity light, you'd get less. But once you went past that frequency, it just stayed the same. And this really didn't make a lot of sense with the classical theories. High frequency light from a dim source gave electron emission without any lag time, and that's not what the theory predicted. So Einstein was trying to explain this, and this is how we got into all this trouble, but it ended up being a good thing. So he said, well, maybe light energy is coming in little packets. And a packet of light is called a quantum or a photon. Where have you heard the word photon? Star Trek. Fire the photon torpedoes, right? Yeah, photons. Well, photons actually exist. A photon is a packet of light. It's a piece of energy, a piece of light. The energy of a photon is directly proportional to its frequency. That makes it inversely proportional to its wavelength. So the energy is proportional to the frequency. This H is a proportionality constant. It's called Planck's constant, after Max Planck, who worked on this as well. And there's its value, and you definitely don't have to memorize that. 6.626 times 10 to the minus 34th joule seconds. So E equals h nu, Planck's constant times the frequency, or E equals hc over lambda, where c is the speed of light in meters per second, and lambda would be the wavelength in meters, because nu is c over lambda. So these are the same thing, right? So if we look at a 100-watt light bulb, radiates energy at a rate of 100 joules per second. And we're telling you here the watt, which is a unit of power. Power is energy over time. Power is defined, the watt is defined as 1 joule per second. So 100 watts means you're getting 100 joules of energy per second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? Yeah, that's supposed to be a period, I think. Assume 3 sig figs. Well, what do we do here? Well, how about we write down those equations from the previous slide? So that's the information we had. So we've got 100 joules per second, and we're wanting to know how many photons are emitted per second, and we've got a wavelength. Well, we have a wavelength. What could we calculate? We could calculate the frequency. Could we calculate the energy? Could we calculate the energy of 1 photon of light? Yes, we could, thank you. So the energy is going to be H, 6.626, times 10 to the minus 34. Joules times second. Yeah, I know it's a weird unit. And what's the speed of light? 3.00 times 10 to the 8th meters per second. And then we're going to divide that by the wavelength. The wavelength is 525 nanometers. Instead of writing nanometers, I'm going to write 10 to the minus 9th meters. So 525 times 10 to the minus 9th meters. Because that's what nanometers is. Look how the units cancel out. The seconds cancel and the meters cancel, and I'm left with a unit of joules. So 6.626, here's another reason we need scientific notation. Calculator can't handle 10 to the minus 34. That's even a crazier exponent than 23. That times 3 times 10 to the 8th divided by 525 times 10 to the minus 9. And we get this ridiculous number that the energy of one photon is 3.786 times 10 to the minus 19th joules. Well, this is saying there's 100 joules per second. So if each photon had this many joules, how many would there be in a second if there's 100 joules per second? Well, we can say that this, I need some space. I need a fatter eraser. We could say that one photon. Well, one photon is equal to that many joules. We could use that as a conversion factor to relate 100 joules per second to photons. This is all dimensional analysis. So they're saying how many photons per second? Okay, well, what we have here is 100 joules per second. We want photons per second. So we want to multiply by photons and divide by joules. And that's what we just calculated here. It would be 1 photon per 3.786 times 10 to the minus 19 joules. And then the joules cancel out. And so we end up with, it's saying 3 sig figs, 2.64 times 10 to the 20th photons. Is that a reasonable number? Think about a 100-watt light bulb. That's a fairly bright light bulb, right? It's radiating light. In a second, you're going to have a bunch of photons, right? You're not going to have less than 1 photon, right? We're expecting this, if a photon is a tiny piece of light, and this light is strong enough that you can see it, there must be a lot of photons, right? Does that make sense? It should be a big number. If you do a calculation like this and you come up with 10 to the minus 20th photons, that would be silly, wouldn't it? In a whole second of this bright light bulb, less than 1 photon of light, that wouldn't make any sense. Any questions about this calculation? This is the sort of calculation that you just have to think about. You have to think about, you have to be comfortable with units and putting things together. Sometimes you just need to write some pieces down and figure out how they work out. In Chem 1A, you cannot just have a set of tricks that you have learned how to do. That may work in 3A, but it's not going to work in 1A because we will definitely ask you to do a brand new trick on an exam. So you have to be able to think. Those electrons that got ejected, how does that relate to the light? Well, one photon at that threshold frequency has just enough energy to dislodge a single electron from the metal. Why do the electrons stay in the metal at all? Well, they are bound to their atoms. And so we use this, I think it was, is that phi or chi? I can't remember. That Greek letter, that guy right there. Theta?
Theta?
No, I think theta's the horizontal one.
Yeah, theta's horizontal.
Theta, this is theta. That's theta. I think it might be, I think it's phi, because I think chi is the x. I think it's phi. Anyway, that guy is the binding energy of the electron. What we see when we irradiate that metal with higher frequency photons is that the electrons absorb more energy than necessary to escape. And the excess energy is just the kinetic energy of the ejected electrons. I don't know why I'm thinking of kids going to a carnival. Maybe because I sat in the car for 2 hours last night while my son was at the Carruthers Fair. Anyway, so you have a child. The Carruthers Fair you don't have to pay to get into, but let's pretend Disneyland. We'll talk about Disneyland instead. This is how my brain works. It goes in these interesting paths. Anyway, so it costs, let's just say, $100 to get into Disneyland. So you've got a kid with $59. Can he get into Disneyland? No. Kid with $100, can he get in? Yes. Kid with $150, can he get in? Yes. What happens to the extra money? He takes it in with him, right? And of course he's going to spend it. But that's like the kinetic energy of the electron. There's this price it has to pay in terms of energy to break free, and then any extra energy is just bonus. So you've got this threshold at Disneyland. You have to have $100 to get in. If you have more, you can still get in. If you have less, you can't. Does that make any sense? So this threshold binding energy, we have to give the electron at least this much energy so that it can get out of the metal. Any extra is just goes as kinetic energy. So we can calculate the kinetic energy of that electron. The kinetic energy is going to be the energy of the photon of light that started it all minus the binding energy of the electron. The energy of the photon is h nu, and this, what I think is phi, is the binding energy of the electron. So let's think about a metal. It will eject electrons from its surface when struck by yellow light. What will happen if it's struck with ultraviolet light? So it can be hard to remember which of the colors is more energetic. I have no problem remembering Roy G. Biv, okay? But then which is more energetic, which is less energetic? Well, then I think about getting sunburned, which, just look at me. That's happened many, many times. Ultraviolet light is the burning light from the sun. Ultraviolet. Ultra, above. It's above violet. It's next to violet. Violet is the most energetic of the visible light. Yellow's kind of in between. So ultraviolet is going to have more energy than the yellow light. So the yellow light had enough energy to get the electrons out. What's going to happen with ultraviolet light? A, no electrons would be ejected. B, they would be ejected, but they would have the same kinetic energy as those ejected by yellow light. C, they would be ejected and have greater kinetic energy than yellow, or they would have lower. C. That was yes. C, it's C. Electrons would be ejected, they would have greater kinetic energy. So even though the electron has more energy, it still pays the same price to the binding energy to get out. The kid who has more money going to Disneyland does not pay more to get into Disneyland than the kid who has less money. But there's this level. So what is just really hard to get your mind around? We call it the wave-particle duality of light. Sometimes light appears to behave like a wave, and at other times light seems to act like a particle. Light acts like a wave. You pass it through a prism and it separates according to its wavelengths. That's wave behavior. And yet it is acting like a particle in that when you shine it on a piece of metal, it ejects electrons based on the frequency of the light, not on the total energy of the light. So it acts like a particle, it acts like a wave, and which behavior you observe depends on what experiment you're doing. Because it has a dual nature, but when you observe it, you force it to behave like one thing or another. Schrodinger's cat.